So how do we implement a graph data structure really, keeping in mind that we want to be able to perform all of those operations from the previous video? Well, we have a few different ways. We could either use what's called an edge list, an adjacency list, or an adjacency matrix. So I'm going to represent this example graph here, which is just a flight network. And I have, this is a directed graph, although we could use the same implementations if we wanted to implement an undirected graph. We want to be able to store this relationship between all of the objects that we have. So we need a way to keep track of all of the vertices that we have and all edges that we have. So let's see, just kind of working our way through this list, what an edge list structure would be. And for each of these, I'm going to give just a few of the methods that we want to be able to implement with this data structure and how we would do that and what the running time would be. So with an edge list structure, we have just a container consisting of all of the edge objects that we have. So we've got one for each of the M edge objects we have. Remember, we have N is how many vertices we have, and M is how many edges we have. So we've got M edges that we keep track of in this container. And for each edge object, we keep track of three things. One is whatever we're storing at that edge. So in this case, we're storing the corresponding flight. And then we keep track of the origin vertex and the destination vertex. So for example, if you look at the previous slide, we had somewhere in our graph an edge from Boston Airport, so BOS, to JFK. And that was our NW35 edge. So that's this first edge here. And how we know Boston BOS was the originating vertex, we have a pointer to it here. So this is referencing that whatever this first one is, this is the originating vertex, and the second one is the destination vertex. So this edge starts with BOS and it ends at JFK. Then in our edge list structure, we also have this collection of vertices. Now, for each of the N vertices that we have, we're not maintaining a reference back to edges. We have only at this point in our edge list structure, this is purely edge based. So we have for edge objects, we have associated vertex objects. But given a vertex object, we don't have this reference to go back to see which edges it's associated with. So the total amount of space that we're taking up, the memory complexity here, we have M edge objects we're keeping track of. Each edge object stores the object, an originating pointer to an originating vertex, a pointer to the destination vertex, and then we have N vertices to keep track of here. So the total space used is big O of N plus M, number of vertices plus number of edges. Now, if we wanted to implement, let's say, incident edges, so this is given a vertex, we want to find out which edges are incident on that vertex, then we could immediately access which vertex we're looking at. However, for a given vertex, even if we were to access it in this container of vertex objects, we wouldn't have a way to go back. So instead, we would have to start with each of the edge objects that we have here, check its origin and destination vertex to see, is this incident on a given vertex? So since we'd have to scan through all M possible edges, the total runtime of this using an edge list structure is big O of M. To check to see if two vertices are adjacent, again, we'd have to start at the beginning of our edge list and work through it to see, is there any edge which has as its origin vertex one of these vertices and as its destination vertex the other vertex. So the total cost there again would be big O of M, because we have to go through all of our edges to find, is there an edge connecting these two vertices. To insert a vertex though, this is pretty easy. We have our container of vertices here. We could just create a new vertex at the end of this container. So this is constant time. And similarly, inserting an edge we can do in constant time because this is as as easy as adding a new object to the end of this, storing whatever we wanted to store that object here, and then keeping track of pointing it to V being the origin vertex and W being the destination vertex. So maybe we have a reference here and then here. So that we can do in constant time. Let's talk about removing an edge next. So if we have exactly that edge that we want to remove, we can access it in constant time inside this container because we're immediately given its position E. So we can remove that edge in constant time. But if we want to remove a vertex, remember that removing a vertex means that we not only get rid of that vertex object, we also get rid of any edges that are incident on that vertex. So while we can access the vertex that we want to remove in constant time, maybe we want to remove LAX, well, if we get rid of LAX, we're also going to have to get rid of this edge, and this edge. And in order to find those edges, we would have to get a list of all of the incident edges corresponding to this vertex and remove each one of them individually. And in order to access all of those, this requires for us to traverse the entire edge list. So this runs in big O of M time. Now you'll notice that some of these operations we could have done a little bit more efficiently, or they would have been a little bit easier if we had stored information additionally for each vertex, which gave reference to what edges are associated with that vertex. And this is what an adjacency list structure does. So this is our adjacency list structure. It looks very much like an edge list structure. Everything up to this point is the same. We have a list of edges. Each edge object consists of a reference to its origin vertex and a reference to its destination vertex. We also have a list of vertices. But then in an adjacency list structure, we store additionally for each vertex a list of all edges that are associated with it. So this will immediately give us access to those edges associated with that vertex. And for an undirected graph, then we have no distinction between incoming edges and outgoing edges. For a directed graph, though, we can keep track of these separately, as here are all of the edges which are incoming into that vertex, and here are all of the edges which are going out of that vertex. Now, similarly, the amount of space that we use is proportional to n plus m. And this is because we have m edges we're keeping track of here, we have n vertices we're keeping track of here, and then the total number of edges that we're keeping track of over here is still m. So we've got 2m plus n. When we put this in big O notation, this is big O n plus n. Now, if we want to figure out for a given vertex what edges are incident on that vertex, then we can in constant time find that vertex that we want to check, and then immediately now we've got a list of here's all of the edges that are incident on it, so we can output all of them. Now how many there are, this is dependent on the degree of that vertex. So we have degree of V, many edges that are incident on V. So the cost of this is just, this operation is just the cost of outputting where all of those edges are. We can check also if two vertices are adjacent a little bit more efficiently now. We have access to these vertices in constant time, and we can check for either one of them. We have a list of all edges. So let's say we wanted to check, let's say for BOS, and also for DFW, we wanted to know yes or no, are they adjacent? So we need to determine, is there an edge which connects those two vertices? Well, we could choose, let's say we could go to BOS airport and figure out here's all of the edges that are incident on it, and see in any of these edges we can in constant time access this edge or this edge, check to see if its other endpoint is DFW, or we could check DFW, all of its edges, and see if any of its corresponding edges go to BOS. But we don't have to check both of them, because if they're adjacent, then they'll both have an edge same edge connecting them. So rather than checking both of them, we're just going to check whichever one has the least number of incident edges. So this will be the minimum between whichever one of them has the smallest degree. So either U has less edges incident to it, or V has less edges incident to it. Whichever one is less, so in this case, BOS has only 2 edges. So we'll just check those 2 edges, rather than DFW, which has 5. All right, now if we want to insert a vertex, similarly, this is as easy as just adding a new vertex to the end of our container. So this is constant time. And inserting an edge we can also do in constant time. This is creating this new edge which stores O, and it'll connect vertices V and W. So we create that new edge here. We reference the appropriate vertices, and then for those appropriate vertices, we add to the end whatever the incoming and outgoing edges are. Okay, and removing an edge, still, we can do this in constant time because we're immediately given that edge, so we have access to that edge object already. And to remove a vertex, we can do this faster now because while we want to get rid of that vertex, we can access the vertex in constant time. We also have to get rid of all edges associated with that vertex. And since we're keeping a list of all edges associated with it, then if we want to get rid of this vertex, we're just going to have to go through each of the edges incident to it and then remove those edges as well. So we can do this in degree of V time. This is how many edges are incident on that vertex. So this is a much better data structure than using an edge list. We essentially have an edge list contained in it. We're just storing a few pieces of additional information, which make it easier to access an element based on its vertex, or to operate directly on given a vertex. But there's one thing here which is sometimes we'll see a few algorithms which use this operation in particular quite frequently, checking to see if 2 vertices are adjacent, and you'll see several problems that do this. And there's one other data structure we'll see of how we could possibly implement a graph which will cost more space. However, it will give us a better runtime to see if 2 vertices are adjacent. And this is the adjacency matrix structure. So the idea behind this is that we have actually now a matrix where we've got each row and column correspond to a vertex. So we could even number all vertices arbitrarily from 0 to n-1. And then we store in each cell of this matrix, we store an edge object if we've got an edge that connects them. So for example, here we're storing NW35, that edge, which originates in BOS Airport and ends in JFK Airport. We've also got the edge, for example, UA120. This starts in LAX Airport and it ends in ORD Airport. Now, there's a lot of space that we're taking up here because we've got a row and column for each of the n vertices that we have. So we have n squared cells, which means the amount of space that we're using is quadratic. And some of it is even wasted space. So notice that we don't have a lot of edges here. So we've got some cells like this one where we're actually not storing anything. But this will make some of our other operations, well, specifically it'll make checking if 2 vertices are adjacent faster. And the reason for that is we're given 2 vertices. Checking if 2 vertices are adjacent is done in constant time by checking, for example, if we want to see if JFK and DFW are adjacent, we'll check at index corresponding to JFK and DFW, is there any edge stored in this cell, yes or no? So because we're just accessing an element of a 2-dimensional array at a particular index, we can do this in constant time. So this is the main reason why we would want to use an adjacency matrix structure, because we can do this operation much faster than in the previous implementations. So let's see how the other methods would be implemented. So if we want to check for a given vertex what all edges are incident to it, well, we can access that vertex in constant time. However, we would have to go through every cell corresponding to that vertex to see what all edges are incident on it. So this would be linear time big O of n in terms of the number of vertices. And if we want to insert a vertex or even remove a vertex, because we're maintaining this large structure, just to straightforwardly insert a vertex, this would mean we would have to create another row of this fixed size two-dimensional array, which means we would have to then create a new matrix of one larger size row and one extra column, copy all of the n squared elements we had from our old structure into the new larger one, which means this would take n squared time. And similarly for removing a vertex. If we get rid of that vertex and then that means we create a new array of one size smaller, just a straightforward implementation of this would be then to resize our matrix. We have to go through all n squared cells. But we can insert or remove an edge in constant time because, again, we're just accessing that particular index of our two-dimensional array. So this is at index v and w, we insert this object, or we remove that particular edge at index v and w, since we can access the endpoints of that edge. Okay, so this is just a summarization of those operations that I mentioned on the previous slides. So definitely we won't use an edge list because for no additional space we can improve some operations. We could use an adjacency list then, or an adjacency matrix. Unfortunately, an adjacency matrix costs more in terms of how much memory we need in order to store it. However, the benefit of it is that we gain that checking if two vertices are adjacent becomes constant time. And we'll see some algorithms where this is particularly beneficial, but again, this is a trade-off that we need more space in order to accommodate that.